A logic problem can be written three ways, and this topic is really about moving between them. There is the logic expression, written in words or in symbols. There is the truth table, listing every possible combination of inputs and what the output does for each. And there is the logic circuit, a diagram of gates with inputs on the left and an output on the right. The syllabus asks you to convert in every direction, expression to table, table to expression, circuit to expression, expression to circuit. So none of these three is the primary one. On notation, in symbolic form and is written as a dot or is written as a plus, and not is a bar drawn over the top. Those symbols are borrowed from arithmetic, but they do not mean multiply and add. A dot means and a plus means or. Start with the circuit because it is the representation most exam questions are built around. Inputs enter on the left as labeled lines. They pass through gates and an output leaves on the right. This circuit has three inputs, A, B, and C, and three gates. To turn a circuit into an expression, work left to right and label each gate's output as you reach it. The AND gate is fed by A and B, so its output is A and B. The NOT gate is fed by C, so its output is not C. Then the gate on the right, an OR gate, is fed by those two outputs, which gives X equals, open bracket, A and B, close bracket, OR, open bracket, not C, close bracket. Bracket every gate output as you carry it forward. Writing A and B or not C without brackets is ambiguous, and it will not be credited. Now let us trace some values through it, because that is the skill an exam actually tests. First combination, A is 1, B is 0, and C is 1. Those three values enter on the left. Work forward one gate at a time. The AND gate has A equal to 1 and B equal to 0, and only outputs 1 when every input is 1. So with a 0 present, its output is 0. Next, the NOT gate. Its input is C, which is 1, and NOT simply inverts, so its output is 0. Now the OR gate, which takes those two gate outputs, 0 and 0, or outputs 1 if either input is 1 and neither is, so X is 0. Now watch what a single change does. Keep A at 1 and C at 1, but change B from 0 to 1. The AND gate now has 1 and 1, so its output flips to 1. The NOT gate is untouched because C has not changed, so it stays at 0. But the OR gate now sees a 1 on its upper input, and OR needs only one of its inputs to be high, so X becomes 1. One input changed and the output changed with it. Trace gate by gate, write each gate's output onto the diagram as you go, and you cannot lose your place. Tracing one combination is fine, but a truth table needs every combination. The method has 3 steps. First, count the inputs. 3 inputs, A, B, and C, means 2 to the power of 3, which is 8 rows. 2 inputs would be 4 rows, 4 inputs would be 16. Second, add intermediate columns, 1 for each bracket in the expression. Here that means a column for A and B and a column for not C. This is the step students skip, and it is the one that saves you. Working out a compound expression in your head for 8 separate rows is how errors get in. Working out 2 simple columns and then combining them is reliable. Third, produce the output column by applying the final gate to those intermediate columns. Let us actually do it. 8 rows, and you list the input combinations by counting up in binary so that none is missed and none is repeated. Row 1, a 0, B0, C0. A and B is 0, not C is 1, and 0 or 1 gives X equals 1. Row 2, 0, 0, 1. A and B is 0, and not C is now 0, so X is 0. Row 3, 0, 1, 0. A and B is still 0 because A is 0, not C is 1, so X is 1. Row 4, 0, 1, 1. Both intermediate columns are 0, so X is 0. Row 5, 1, 0, 0. A and B is 0 this time because B is 0, but not C is 1, so X is 1. Row 6, 1, 0, 1. Both intermediates 0 again. X is 0. Row 7, 1, 1, 0. Now A and B is 1 and not C is 1 as well, so X is 1. And row 8, 1, 1, 1. A and B is 1, not C is 0. but OR needs only one of them to be high, so X is 1. Now look down that output column. X is 1 whenever C is 0, and also whenever A and B are both 1. That is the expression, read straight back off the table. Going the other way, table to expression, has a method that always works called the sum of products. 3 steps. 1. Look only at the rows where the output is 1 and ignore every row where it is 0. 2. For each of those rows, write one term that ANDs all the inputs together, putting not in front of any input that is 0 in that row. 3. Or all those terms together, because the output is 1 if any of those rows occurs. On our table, 5 rows give an output of 1. The first is A0, B0, C0, which becomes not A and not B and not C. The next is not A and B and not C. Then A and not B and not C. Then A and B and not C. And finally, A and B and C. All those 5 terms together and you have a valid expression. Now, that is a mouthful, and the obvious question is why it does not look like the short expression we started with. Both are correct. They produce identical truth tables. They are the same function written 2 ways. Sum of products guarantees you an answer, which is what matters under exam pressure. It does not promise the shortest one. Unless the question asks you to simplify, a correct sum of products expression earns the marks. And the last direction, expression to circuit. Work outwards from the brackets, exactly as you would evaluate arithmetic. First, draw the inputs as labeled lines down the left-hand side, 1 per variable. Second, draw a gate for each bracket. Because brackets are evaluated first, A and B becomes an AND gate fed by A and B, and not C becomes a NOT gate fed by C. Third, draw the gate that joins them. The OR sitting between the 2 brackets becomes an OR gate fed by the 2 gate outputs. Fourth, label the final output X, and then check that every input you listed is actually connected to something. A dangling input line is a common slip, and it is easy to spot if you look for it deliberately. One detail on circuit diagrams that costs more marks than anything else in this topic. NAND and NOR are not drawn as separate shapes. A NAND gate is drawn as an AND gate with a small circle, a bubble, on its output. A NOR gate is an OR gate with the same bubble. That bubble is the NOT. Look at the second circuit on the page. The gate on the left has the D shape of an AND gate, but there is a bubble on its output, so it is a NAND, and its output is NOT, open bracket, P and Q, close bracket. Miss that bubble and you will read it as a plain AND. And because NOT inverts everything, every single value in your output column will come out wrong. So before you start tracing any circuit, scan the gate outputs for bubbles. 4 habits to take into the exam. First, always draw intermediate columns, even when the question does not ask for them. They cost you nothing and they stop compound expressions being evaluated in your head. Second, list input combinations by counting up in binary 000, 001, 010, so that no combination is missed or duplicated. Third, when reading a circuit, write each gate's output onto the diagram before you combine anything. Fourth, check every gate output for a bubble before you trace a single value. And remember the direction the question is actually asking for. Circuit to expression, table to expression, expression to circuit, and expression to table are 4 different tasks and each has its own method. Read which one you are being asked for before you start writing.